All right, here's our last method related to finding generation and consumption in a problem. So our last method is extent of reaction, and this is different from what we've seen before. We no longer have the general balance equation. We now are using a different way of finding a series of equations. So essentially, atomic balances and molecular balances use the general balance equation to set up a set of equations, a system of equations. Extent of reaction does not use the general balance equation. It uses a different equation. And so it's always going to be in terms of molar amounts. It can be in terms of molar flow. So keep in mind that you can have an end or an end dot. So let's take a look at this new equation. Our new equation says that N sub I, which is the number of moles of a species, I is your species, at a given time, is equal to the number of moles of that same species initially plus or minus V sub I, which is the coefficient of the balance reaction of that species, times what's called an extent of reaction. Okay, so let's go through some of these terms really quickly. So number of moles initially, we can find that. That might be what's coming into the system, right? It could be the input to the system. And then the number of moles at a given time could be what's generated through the equation, or we could be looking at the output. It kind of depends on the problem. The coefficient of the balanced reaction can either be positive or minus, and we will see which is which in just a second. Extent of reaction basically is a way of saying how far does that reaction go towards completion. Okay, one of your pre-lecture questions is going to be to explore this a little bit more. What does this actually mean in chemistry? So do a little bit of research on that. Let's look at the degree of freedom analysis for extent of reaction. It's different again. So remember, I may ask you for one of those three methods on the assessment, and you need to be able to do degree of freedom analysis for each. So this is a good thing to have on your notes for your exam. Okay, we start with the number of labeled unknowns as always. Then extent of reaction is similar to molecular balances. We add the number of independent reactions that are occurring. That's going to account for the fact that side reactions occur in real life. There's multiple reactions that can move through a system. Okay? Then we subtract the number of independent reactive species or molecules. This is the same as saying let's subtract everything that's participating in the reaction. Okay, so it's just like the species we've seen before, but we're now looking at the reactive species particularly. Because then we're going to subtract off the number of independent non-reactive species. This should say non-reactive here, so make that change in your notes. The reason that we subtract off the non-reactive values is because they have no extent of reaction. They're not reacting, so there is no E value associated with them. Then, as always, we subtract off any other equations and relations we have to get the number of degrees of freedom. Okay, so key difference here is you're adding in the number of reactions, and then you're differentiating between your reactive and non-reactive species. So our procedure for extent of reaction, same as always. We balance the chemical reaction, we perform a degree of freedom analysis. That's not changed. Okay, then we identify the molecules that are present. Remember, we're not using atoms at this point. Then we use our new equation for extent of reaction, and we write an equation for each molecule. Okay, you will often not know what E is, but you can find it based on your system of equations. So that's really important. So you don't always get given what E is. Sometimes we can find it, but sometimes we can't. And so we're going to want to watch out and make sure that we have an E for every single equation. Okay, now here's one thing that's important that's not on this slide. You have a different extent of reaction for each reaction you have. So if you only have one chemical reaction, you only have one E. But if you have two chemical reactions, you have two E values. So you need E1 and E2. So make sure that you're aware of that. We're going to practice this a little bit in class. Okay? And then promise that I would tell you when VI is positive and negative. VI is positive for products because they are being generated. Okay, so you're adding more. That's how you remember that. And then V sub I is negative for reactants because those are going away. Those are what's being consumed. Okay, so it's a plus or minus in the equation, and you need to determine if it's plus or minus based on whether or not it's a reactant or a product. And then as always, we solve for any unknown variables. So let's go back to our favorite example, dehydrogenation of ethane. Same problem that we've seen in the past two pre-lectures. Input of 100 moles per minute, output observed of 40 moles per minute of H2. The input is C2H6. This is the reaction that's occurring, and we want to find out how much ethene and how much ethane are in the output. So same problem setup. This has not changed, okay? So this will always be something that I'm asking for on an assessment because this doesn't change regardless of your method. So if we can set this up, we're in a good shape to use one of our methods. So there's your balanced equation. There's the same flow diagram that we've been seeing. Remember that A is going to be C2H6, B is going to be C2H4, and C is going to be H2. All right, let's do our degree of freedom analysis. So we have two labeled unknowns, the two output molar streams we're looking for. We have one independent reaction. We have 3 reactive species, 0 non-reactive species, and 0 other pieces of information. So we already knew this was a solvable equation, but it's good to check as always. So yes, this is a solvable problem. There we go. All right, let's finish by going through how to solve the same problem, but with extent of reaction. All right, so let's start with C2H6, okay? Extent of reaction. We do not know what the final amount of N sub A is. We don't know. We know the initial amount of A is equal to 100 moles per minute because that's what's being fed. And then we have a balanced equation. So we know V sub A is equal to 1. And the negative comes from the fact that C2H6 is a reactant. That's negative. So our equation using extent of reaction looks like this. N of A at a given time is equal to 100 minus the extent of reaction. Again, we don't have E yet. We don't know what it is. So we only have one equation. We need to write another extent of reaction to be able to solve because we don't know what E is right now. Okay, so let's take a look at that. All right, so let's write the extent of reaction for H2. Okay, if we look at H2, okay, C is representing H2. At some time coming out of the reactor, we have 40 moles per minute. We did not feed anything to the reactor, so initially we have 0 moles per minute. We have a V sub C equal to 1 because there's a coefficient of 1 in front of the H, but now it's a positive because H plus is being generated. So what that means is that 40 is equal to 0 plus 1E, so that means extent of reaction is equal to 40 moles per minute. So you just found E. How cool is that? You're like, that's not cool, Dr. Lane. I'm just watching the video because I have to. I get it. It's all right. So let's keep going and let's find the extent of reaction for C2H4. Okay, we don't know what NB is at some time. We know initially it's 0. So then we go down here and we find our coefficient. It's positive 1 again, positive because it's being generated. So the equation here is that NB equals 0 plus 1 extent of reaction, so NB equals the extent of reaction. So let's put that all together on the last slide. Okay, N sub A is equal to 100 minus E. That's our first equation. Second equation is that 40 is equal to the extent of reaction. Third equation is that NB equals the extent of reaction. So therefore, N sub B is equal to 40 moles per minute and N sub A is equal to 60 moles per minute. And if you check, these are the exact same answers that we got when we did this with atomic and molecular balances. Remember, you should always get the same numbers regardless of the method. Okay, so a quick recap on extent of reaction. Okay, degree of freedom analysis is different. It looks very similar to your molecular balances. You only do extent of reactions on reactive species, and this is a new way of writing a system of equations. We have to be very careful about signs of V sub I, that's important to us, and then we may or may not have the E value for extent of reactant, and we may have to solve for it, or we may be given it. So we're writing a system of equations. You're probably going to have to write all of the equations before you can solve most of the time with this method, whereas sometimes you can find intermediary steps with our other methods. So looks a little bit different. Again, make sure that everything makes sense to you. We'll practice this again in class so that you have an example of this with multiple reactions.